Welcome to the Problemers Channel Season 2, Episode 29, the episode which I titled Magic Squares of Odd Orders, because in this episode we will study a linear algorithm for construction of arbitrary magic squares of odd orders. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section find the episode titled The Problemers Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we motivate and explain everything that we do on this channel. The challenge in the mathematical problem S2E29 was to find a mechanical way or an algorithm for constructing arbitrary magic squares of odd orders. Before we deep dive into the discussion of such an algorithm, I would like to describe a small number of basic definitions that pertain to magic squares. Since the main culprit of this episode is a square, a few words about a square and about a way in which the square can be constructed. All the constructions that I will describe in this segment can be carried out with the Euclidean straight edge and compass. So here is a descriptive way to construct a square. That, by the way, is very similar to a way in which in topology it can be shown that any closed planar curve can be trapped inside of a square. In other words, in order to construct a square, we draw one straight line. Let's say this one. I'll draw a blue straight line number 1 and some d units of distance. Let me mark it with white. D unit of distance away from the first straight line, where d is greater than 0. We construct another straight line that is parallel to the first one. We do it like so. So now we have two straight lines that are parallel with respect to each other and that are displaced from each other by d units of distance apart, and d is a strictly positive real number. Then we pick any point anywhere in the plane that is equidistant from these two straight lines, let's say this point, and then we execute the following maneuver. We rotate the plane around that point by pi over 2 radians or 90 degrees, counterclockwise or clockwise, and we obtain what? We obtain two new straight lines which will be positioned, let's see, this way and that way. Let's pretend this is a square, and then since this distance is d units apart, then this distance in theory is supposed to be also d units of distance. And then since this is d units of distance and this is the d units of distance, then the resultant shape will be precisely a square. But this is mostly a descriptive way. So here is a way to construct a square that is slightly more algorithmic. Let's say in first we draw a straight line like so. Then on that straight line we pick 2 points. Let me use red chalk, for example. This point and this point, and the distance between these 2 points will be precisely the length of the side of a side of the target square. Then, centered at one point, we draw one circle that passes through another point, and centered at another point, we draw another circle that passes through its body point. So we'll do it this way, let's say. These two circles will intersect at 2 points. We are only interested in one. Let's say we pick this point. And then through this point, centered at this point, we construct a circle that passes through these 2 points. That can be done always, and the idea here is the following. Let's say this circle will look something like so. Let's pretend that this is a circle, and the idea here is the following. The straight line through this point and the center of the biggest circle will be drawn that way, and this straight line will be what? It will be diameter of the biggest circle, and this will be a chord, so this angle over here must be right. Likewise, if we draw this straight line, it will intersect the biggest circle over here as well. That straight line must be also perpendicular to our original straight line. Of course, my drawing over here is horribly out of proportion and out of scale, but the idea is that these two straight lines will intersect our first two circles at 2 points, here and here, and precisely the straight line through these 2 points will generate a square. It doesn't look like when drawn by hand, but in reality that's what it will be. Now we can also, with the Euclidean straight edge and compass, divide any side of the parent circle in equal number of line segments of equal length on one side, and let's say on the other. Connect these straight lines this way, divide the other side also in the same number of equally sized line segments, and that way we can generate a square that will be n times n for any n that is strictly greater than 0, 1, 2, 3, 4, 5, and so on. That can always be done. Now, for a tiny bit of historical trivia, in the year of 1672, simultaneously in Copenhagen and in Amsterdam, a book titled The Danish Euclid was published in Danish and in Dutch. And that book was written by a Danish mathematician. His name is spelled over here, Moore. And in that book, Moore published a proof that showed that any construction that can be done with the Euclidean straight edge and compass can be done with a compass alone. And 125 in 1797, 125 years later, an Italian mathematician who goes by the name Mascheroni apparently also rediscovered the same proof. Now the theorem carries the name of both of these mathematicians, Moore and Mascheroni, and that theorem states precisely that any construction that can be carried out with the Euclidean straight edge and compass can be carried out with a compass alone. Yes, admittedly, in practice, these constructions with a compass alone become quite involved. They're quite bulky and most of the time quite awkward, but theoretically still it is interesting that any construction that can be done with a straight edge and compass does not really need a straight edge, and in such constructions we use a straight edge for convenience and aesthetic reasons, if you will. So that way we explain how an n by n, an arbitrary n by n square can be constructed. And evidently, this construction can be carried out for any whole positive number, 1, 2, 3, 4, 5, and so on. We can do that for as long as our heart desires. And now that we have an n by n square that has n rows, n columns, and consequently how many? Evidently n square smaller squares or n square cells. Then these cells or smaller squares can in theory be filled literally with anything. It is possible to fill these cells of the parent square with bananas, porcupines, and guitars. But if each and every cell in that square is filled with a number in general or with a whole number in particular, then such a square becomes a number square or a numeric square. And now we need to pay close attention, because in some sense the numbers that can be put into the cells of the parent magic square can do not really have to be consecutive numbers. 1, 2, 3, 4, 5, and so on to n square. This is a traditional way to fill out the upcoming magic square, but in general, the elements or consecutive elements of any arithmetic progression can be used in order to construct a magic square. And traditionally, or in some sense, the sequence of numbers 1, 2, 3, 4, 5 is perhaps one of the simpler or the simplest arithmetic progressions. And these are the numbers that most people work with, and these are the numbers that we will work with in this episode. Wonderful, we now know how to construct a square using the Euclidean straight edge and compass, or a compass alone. We know how to partition that parent square into n square equally sized cells. We know that if we place certain numbers into such a square, then it becomes a number square or a numeric square. And now the next question is, let's say we fill in our favorite numbers 1, 2, 3, 4, 5 into the cells of our parent square, like so: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. Will this numeric square be a magic square? So this is the interesting and important question on the answer to which everything else pivots when it comes to the business of constructing magic squares. A numeric square becomes a magic square if and only if the following four conditions occur. And these four conditions are actually very important, because the traditional way of proving that any linear algorithm according to which a magic square of an odd order is constructed is correct and valid is based precisely on these four conditions, and these four conditions go deep into validating such algorithms. And in such algorithms, for example, in such proofs, certain determinants show up, and these determinants show up because two linear congruences show up in the corresponding proofs, and these linear congruences show up because we need two numbers to describe the position on every cell. For example, the proverbial x and the proverbial y coordinate of such a cell within the parent square, and from this pair of linear congruences out pops a determinant, and when certain conditions for that determinant hold, then evidently it can be proved that this or that algorithm for generating a magic square of an odd order is correct and valid. So what are these four conditions? Well, the first condition states that the sum of all the numbers in all n rows of a numeric square is one and the same number, s. That's the condition number one. We'll just designate this number as s. Condition number two states that the sum of all the numbers in all the columns of a numeric square, so let's say that's the sum in rows and that's the sum in columns, is also one and the same number, and that number is not just some any random number, but that number is the same s. So this number over here is one and the same. And what is the third condition? The third condition for turning any numeric square into a magic square says that the sum of all the numbers, the third condition, the sum of all the numbers in the main diagonal of a numeric square, and the main diagonal runs from northwest to southeast in such a square using cardinal directions. So let's say we'll call it main diagonal, is also the number s from the previous two conditions. The fourth and the final condition for flipping any numeric square into a magic square is the following: the sum of all the numbers the sum of all the numbers in the secondary diagonal of the parent square. And what is the secondary diagonal of a square? The secondary diagonal of a square is a diagonal that runs from northeast to southwest in such a square. So the sum of all the numbers in such a secondary diagonal is also S. It's one and the same number. In other words, the sums in all four conditions shown over here must actually be one and the same number S. Consequently, you may suspect that this number S has a special name to it, and it does. What is that number called? The number S that figures prominently in all four conditions is called the magic square constant. In other words, now we understand that if we construct a square, partition it into n square equally sized cells, fill the cells with numbers, and the numbers in such a square obey all four conditions, not just one or two, all four at the same time, then such a numeric square is called a magic square, and the number S, which figures prominently in all these four conditions, is called the magic squares constant. What do you think? Can something that is computationally interesting and meaningful be said about the constant of a magic square if the only information that is known about that magic square is its size? And of course, if we know the type of numbers that make this numeric square a magic square. Let us think about this together. We know that according to definition, a numeric square becomes a magic square if all four conditions shown over here hold. And what does that mean tactically for us? Well, if we sum, according to the first condition, if we sum all the numbers in the first row in all n cells of the first row, let's say we sum the numbers this way, what do we get? We get S. And if we sum all the numbers in the second row of that magic square, what do we get? We get S. And if we sum the numbers, all the numbers in the third row, we get S, and so on. And if we sum all the numbers in the bottom row, the nth row, let's say, we also get the number S. What does this observation suggest? That observation suggests that the sum of all these numbers S, from the sum of the numbers from the first row, the sum of the numbers from the second row, and so on, the sum of the numbers from the nth row will be what? Will be n, let's write it down over here, will be n times S. That's on the one hand. On the other hand, we already observed in the previous segment that in theory or in general, the consecutive elements of any good old arithmetic progression can be used in order to generate a magic square. And what matters in such numbers is that the distance between the immediately adjacent numbers is fixed and one and the same. That means, for example, that we can take numbers such as 57, 60, 63, 66, and so on to all the way to whatever n square numbers that we choose, and we can use these numbers to generate a magic square. But traditionally, we work with the numbers with consecutive positive whole numbers, 1, 2, 3, 4, 5, and so on. So in this case, if we do that, and in this episode we will do precisely that, and we will work strictly with this type of numbers. When we add the numbers in all the rows as described over here, what will we get? Well, in some sense, our numbers that are shown over here in their natural order, 1, 2, 3, 4, 5, will be somehow hashed together. But if we can realign them in such a way that they follow their natural order, which can always be done, the positive numbers commute under addition. In other words, for any two positive whole numbers, a plus b is b plus a. So what does that mean? That the sum of all the numbers in all the rows is S on the one hand. On the other hand, what do we get? Well, we get the sum of n square numbers, and we can write down the formula for that sum. This will be k, where k runs sum of k, where k runs from 1 to where? To n squared. Exactly. First n squared whole positive numbers, starting with 1, 2, 3, 4, 5, and so on to n squared. That formula is known. We can write it down right away. It's n squared times n squared plus 1 over 2. And now when we juxtapose the left-hand side of this equal sign with the right-hand side, what can we say over here? What is s? Well, one copy of n cancels out. And what do we have for s? For the constant of a magic square of order n, if we use consecutive whole positive numbers to generate the corresponding magic square, well, we get that Sn is what? N times n squared plus 1 over 2. Let's write it down over here. The constant of a magic square will be n times n squared plus 1 over 2. And now that we have a way to compute the constant of any magic square, we can describe an algorithm according to which an arbitrary magic square of an odd order can be constructed. The algorithm for constructing arbitrary magic squares of odd orders that we will consider in this episode, to the best of my knowledge, belongs to a French mathematician whose name is written down and spelled in the upper right corner of your monitor, Claude Gaspar Bachet. He lived between the years of 1581 and 1638. When exactly did he come up with the algorithm that I'm about to describe, I'm not sure. Evidently, it happened sometime between the years of 1581 and 1638. But if someone in our community does know when Bachet came up with this beautiful algorithm, then by all means, do not be shy. Share that information with our community in the comment section to this episode. And again, if you manage to solve this problem correctly and on your own, then evidently you are doing pretty good. The algorithm due to Bachet for constructing arbitrary magic squares of odd orders has the following 4 steps. In the first step, we are to construct an empty n by n magic square, which we explained how to do in the previous segment. In this episode, and as far as the Bachet algorithm is concerned, we're dealing only with squares n by n, where n is an odd number, and in this case, the linear size of the underlying or parent magic square is called the order of that square. Consequently, the order of all squares that we are dealing with in this episode and to which the Bachet algorithm is applicable must be odd. An odd number traditionally can be represented as 2 times m plus 1, where m is a suitable integer. And again, in this case, n is called an order. And in the first step of the Bachet algorithm, we're to construct an empty 2m plus 1 by 2m plus 1 square, as shown over here. This is a sample empty square, 5 by 5. In this case, the order n is 5. The suitable integer m is 2. 2 times 2 plus 1 is 5. So in the first step, we construct an empty n by n, or 2m plus 1 by 2m plus 1 square, with n square smaller squares or n square equally sized cells positioned inside the parent square, is shown over here, and we explained how to do that in the previous segment. The second step of the Bachet algorithm is a absolutely beautiful illustration of the scope expansion or expand and conquer problem solving approach, because in that step, for each side, this symbol over here means for each. So in the step number 2 of the Bachet algorithm, for each side of the parent magic square that we constructed in the previous step, the step number 1, we are to construct m layer pyramid, or an odd m layer pyramid, according to the following rule. The very first layer of that pyramid uses the corresponding side of the parent magic square, for example, is shown over here, as its base. And in every consequent layer of such a pyramid, we will have 2 times m minus 1 and in the next layer 2 times m minus 3, and in the next layer 2 times m minus 5 squares. And the squares are positioned in such a way that the number of the squares is odd, and they skip one from each side, one square from each side of the previous layer. For example, in this layer of this pyramid, we have 3 squares positioned symmetrically with respect to the central column of the square, and the next square is positioned on top, also 1 square skipped from each side. The number of the squares is odd. In this case, it's 1. And this is how this pyramid is constructed until the number of squares that sits on the very top is 1. This is the final, or the top, logical top of the pyramid. And we repeat that step for all 3 remaining sides. On the right hand side, on the bottom, and on the left hand side, we position exactly the same pyramids in the step number 2 as we just described. And again, this is precisely the step where the scope expansion or expand and conquer problem solving approach manifests itself. Why? Because precisely, let us be realistic and frank, when we look at a way to fill out a given magic square, then somehow, again, consciously or unconsciously, willingly or unwillingly, we box ourselves into a given square, and many people do not even have idea that we should really step outside the proverbial box, or in this case, this box is quite literal, so not that many people have an idea to step out of the box and into the surrounding plane. And this is precisely what the Bachet algorithm does. It expands the scope of the local material. Instead of dealing just with the square as it is given to us, we start using the ambient plane, the parent plane, around and outside of the parent square in the manner shown above. I hatched this square slightly so that you guys can see easily what is the parent square and what is the material that is located outside of that square. Wonderful. In the step number 3, we pick any one of these 4 pyramids that we constructed in the step number 2, and once we pick any one, which one, it doesn't really matter, we pick one, and with the chosen pyramid we pick the very last, so to speak, layer that has precisely 1 square. For example, let's say we pick this square over here, we pick this pyramid, and within this pyramid we pick the top square. And according to the step number 3 of the Bachet algorithm, we quite mechanically, without paying much thought or much attention to what is going on, we simply fill out the numbers, consecutive numbers 1, 2, 3, 4, 5, and so on, mechanically in one chosen direction. Which direction we choose, again, does not matter. We have a certain degree of freedom. For example, we can go from northwest to southeast, or we can go from northeast to southwest in this direction. Which direction we pick does not matter, but once we pick one direction, we stick with that direction for the entire duration of the remaining steps of that algorithm. So here we fill out the numbers mechanically in this diagonal fashion. Then we skip every other diagonal. In other words, this diagonal we skip, and we fill out the numbers in this diagonal like this. We skip this diagonal here. We fill out the numbers in this diagonal. We skip this one. We fill out the numbers in this diagonal, and so on. For example, just to show you some numbers, we will fill out the numbers like so. 1, 2, the numbers that are located outside the square I'll show in red, and let's say the numbers that are located inside the square I'll show in yellow, just for some contrast. 3, the next number will be 4, the next number will be 5. Here we skip this diagonal, we start going 6, and then here we will go 7, 8, 9. This number will be outside, so it will be 10, and so on. And we keep going in that fashion all the way until we fill out all n square numbers depending on the size of our square. Again, out of 4 pyramids, pick one. Start with the topmost square, the single square. Out of 2 possible directions, pick one and stick with that direction for the entire duration of the algorithm. Fill out the numbers mechanically, skip every other diagonal. This is the step number 3. And in the step number 4, in some sense, we unroll or undo the effects of the expand and conquer or scope expansion problem solving approach. And what do? Exactly, we take all the numbers that are located outside of the box, or all the numbers that are located outside of the given parent magic square, and we bring these numbers into the square, into the final positions that these numbers will occupy within the magic square, according to the following rule. The number that sits outside, any number that sits outside of the given magic parent square, is translated vertically or horizontally, as the case may be, precisely by the number of squares that is equal to the order of the underlying magic square. We will see how that works, but for example, just to give you one straightforward demonstration, let's say we take number 1 shown over here. The order of this magic square is 5, and because this number sits above the topmost edge of our square, we will translate this number vertically along the proverbial y-axis by how many squares? By 5 squares, because the order of that sample or demonstration square is 5. So we go 1, 2, 3, 4, 5. Boom, done. The number 5 is, the number 1 is written in, and this is its final place. So in other words, we translate this number here by exactly 5 squares, and we repeat this operation for all the numbers. And here it should be evident and clearly understood that all the numbers that sit to the north of the northern and to the south of the southern border of the given magic square will be translated which way? Vertically along the proverbial y-axis. And all the numbers that sit to the west of the western and to the east of the eastern border of the given parent square will be translated how? They will be translated horizontally along the proverbial x-axis, and all these translations are carried out with respect to one and the same number, where I should underline this right here by n squares. That is the important bit. The amount of squares by which we translate each and every number that is located outside of the square always remains one and the same number n. And do not worry, we'll look at several examples. You will see how exactly does it work. And we will begin our demonstration with a 3 by 3 magic square. Applying the Bachet algorithm to a magic square of order 3, we have the number 3 can be represented in the form 2 times m plus 1 as what? 2 times 1 plus 1. That means m is equal to 1. And we right away know that in the step number 2 of our algorithm, we will have precisely one layer in each diminishing pyramid. But for now, we want to compute the constant of the magic square of order 3. What is the value of that constant? When according to our formula that we deduced earlier, S3 will be what? 3 times 3 squared plus 1 over 2, 9 plus 1, 10 over 2, 5 times 3 is 15. So the constant of this magic square, the magic square of order 3, is 15 if we are to fill our magic square of order 3 with consecutive positive numbers 1, 2, 3, and so on till 9. And again, for those in the know, S3 looks like a finite symmetric group S3, but it is not. This is just a way to designate the constant of the magic square of order 3. Consequently, as the step number 1 of the Bachet algorithm, we construct an empty square that is precisely what? 3 by 3, shown over here. I'll do a little bit thicker lines, and this completes our step number 1. Applying the second step of the Bachet algorithm to our 3 by 3 magic square, or a magic square of order 3, we need to step through all 4 sides of the parent 3 by 3 square and construct 4 odd diminishing pyramids according to the following algorithm. In each such odd diminishing pyramid, the word odd means that the number of squares in each layer of such a pyramid varies as an odd number: 1, 3, 5, 7, 9, 11, 13, and so on. And the number of layers in such a pyramid is given by the number m, which is a suitable integer in the decomposition of the given order of the magic square, which is 3, as 2 times n plus 1. Since the given order of the magic square is 3, and in the format 2 times m plus 1, such a number is represented which way? 2 times 1 plus 1, where m is equal to 1. We already know right away that in this step there will be one layer in each of the 4 pyramids, and that layer will contain exactly 1 square. Consequently, we do so carefully, let's say in the clockwise fashion. We draw 1 square on the north side of our parent square. We draw 1 square on the east side of our square. We draw 1 square on the south side of our square, and 1 square on the west side of our square. And again, one more time, this step, the step number 2, is precisely the explicit manifestation of the expand and conquer, or scope expansion problem solving approach, where we increase the scope of the local material. We step out of the proverbial box, and in this case, quite literally, we step out of the 3 by 3 box. And so that you can see it better on your screens, I will lightly hatch the squares that sit outside our parent square so you can see them better. The southern square and the western square, like so. In other words, this area over here depicts our parent 3 by 3 square, and the 4 squares located on each side of the square outside the square represent specifically the expand and conquer problem solving approach, where we take the local material and we step out of the box and use the extra space outside our square in the ambient plane. And now we move on to the step number 3 of the Bachet algorithm. Applying the third step of the Bachet algorithm to the magic square of order 3, we fill out the numbers in the structure that we constructed in the previous step quite mechanically, and we have some degree of freedom over here. That is, as an initial square or as an initial pyramid, we can pick any which one of the 4 pyramids that we constructed in the previous step. And for a direction in which the numbers will be filled out, we also have choices. We can go, for example, from the direction of northwest to southeast, or we can go in the other direction, for example, from southeast to northwest. Here, for demonstration purposes, let's do something uncomfortable. For example, we will pick an awkward or inconvenient square. Let's say this one, the bottom one. And we will go in the direction from southeast to northwest. In other words, we will go in this direction, but once we pick such a direction and once we pick an initial square, we stick with that direction, we stick with that square at all times for the entire duration of the remaining part of our algorithm. Here, for you guys to see these numbers better, the numbers that will be located outside of the parent square I will show in red, and the numbers that will be inside the square already I will show in, let's say, yellow, just to create some contrast. So here we go number 1. Here we go number 1. Then moving diagonally, we put number 2 next. This is a mechanical process, but this number will be inside the square, so we mark it with yellow. The next number will be 3. It will be located outside of the square in the western helper square, and because it's outside, we mark it with red. This is 3. Now the next diagonal, remember, we skip and we move on to the next diagonal. Here the number will be what? 1, 2, 3. This will be number 4. That number is already inside the square. We mark it with yellow color, and we move again in this direction. Remember, we're moving southeast to northwest, and we do that at all times. We had a choice. We could have went from southwest to northeast, but here we went southeast to northwest, and that is how we move all along the diagonals of the square at all times. So the next number will be 5, and we fill out the numbers diagonally. 5. The next number will be 6. It goes over here. The next diagonal we skip. We jump to the next one. So what will be the next number? 7. That number is outside. We mark it with red. And again, we move in this direction from southeast to northwest consistently this way across all the diagonals. The next number will be what? 8. It is located inside the square. We mark it with yellow, like so. And the last and the final number, the n square, or 3 square, is 9. The number will be 9. It is positioned outside the square. We mark it with red. So this is number 9. This completes our step number 3. And just one more time, out of all 4 pyramids that we constructed previously, we pick one. In such a pyramid, we start with the top, logically top sole square. We will see more of the squares in the next example when we will be constructing a magic square 5 by 5. And we pick any one direction of the 2 possible. We can go from, for example, southeast to northwest, or we can go southwest to northeast. Here, for demonstration purposes, we pick the direction from southeast to northwest, and skipping one diagonal in each iteration, we mechanically fill out consecutive numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9. Game over, and we are ready to move on to the step number 4, which is the final step of the Bachet algorithm. In the step number 4 of the Bachet algorithm, the final step of that algorithm, we manufacture the final product of that algorithm, or a magic square of order 3. And in that step, we roll through all the numbers that sit outside of the parent square, and we move these numbers inside according to the following rule. In general, the Bachet algorithm is quite flexible, meaning that our parent square can be positioned in the parent plane any which way, tilted this way or tilted this way, but there is evidently no reason to torture ourselves with these funny positions. We take a traditional position where we have northern, southern, and then western and eastern, or top, bottom, right, left sides, so that, for example, the sides of this square can be aligned with the traditional, with the axis of the traditional x or y orthogonal coordinate system. And then we perform the following maneuver. All the numbers that sit outside of the parent square on the top side, above the top side, and below the bottom side are translated vertically by the number of squares that is equal to the order of the parent square. In this case, the order of the parent square is 3. And that, what does that mean? That means that we grab each and every number that sits, for example, below the bottom or below the southern border of our square, and we translate that square by 3 squares. For example, we take the square number 1. That number will now be sitting inside the square in its final position, or its final resting place, so to speak, and we count 1, 2, 3. Boom. The number 1 goes over here, and maybe with the with the red chalk, I will show in very light dotted line that we bring this number over here from here to here. How many squares? 3, the order of the parent magic square. 1, 2, 3. So we're done with all the numbers that sit below the bottom border of our square, and we do the same to all the numbers that sit above the top or above the northern border of our square. There is only one such number. That number is 9. So we parallel translate it vertically by the order, by the number of squares that is equal to the order of the parent magic square, which is 3. As such, we go 1, 2, 3. Boom. Number 9 goes over here. This is the final place. This is the destination of the number 9. And again, in light dashed strokes, I will show that this number is translated precisely over here, so you can see how this whole thing was constructed. Now we do the same thing for the numbers that are located outside of the parent magic square on the western and on the eastern, or on the right and on the left side of the square. Here again we have only one number. Let's take care of number 3. Number 3 sits over here, and these numbers that sit to the left of the left side and to the right of the right side are translated which way? They're translated horizontally along the proverbial x-axis. By how many squares? By the number of squares that is equal to the order of the parent magic square, which is in this case 3. So we translate 1, 2, 3. Boom. Number 3 took its final position. Again, how did we obtain it? We translated that square by 3 squares, and boom, it came over here. Now the only one number remains that sits outside the box, so to speak. That number is 7. So we do with this number 7 the same thing that we did with number 3. We grab it and we translate it horizontally along the x-axis by 3 squares. We count 1, 2, 3. Bam, number 7 takes its final position. Now this is the resting place, and I will leave these numbers colored that way specifically so that it's easier for you to keep track of what just transpired. Again, just to show this lightly, not to produce too much mess, the number 7 came over here from this place over here. And we are done with the magic square of order 3. Evidently, this is not the unique configuration. Just by, for example, by using this distribution of numbers, we can do what? Rotations and reflections. And now we're stepping a little bit into the theory of groups, but I will not overload this conversation with too many technical details. But we can check, for example, 6 and 1, 7, 7 is 8, 15, 7 and 5, 12, and 3, 15, 2 and 9 is 11, 11 and 4, 15, vertically 13, 15, vertically 6 and 9, 15, vertically this way with this column 11 and 4 is 15 again. This is our constant of the square because we filled it out with consecutive positive numbers. And along the main diagonal we have what? 6 and 5, 11 and 4, 15, 8 and 5, 13, and 2, 15. Along the secondary diagonal, problem solved. A magic square of an odd order of order 3 is generated. And here, before we start working with the magic square 5 by 5 or a magic square of order 5 in the next segment, what I recommend that you guys do is that instead of picking this square, you pick some other square, and instead of going in this direction, you pick some other direction, and witness the fact that you will still generate a legal and a valid magic square of order 3. Run through the numbers, sum them horizontally, vertically, and diagonally, and prove to yourself that as a sum you will obtain precisely the constant of the magic square 3 by 3. And before we move on, one more word. Let me, for example, use the green one. The central square of the magic square, or the central cell, if you will, has an interesting property. As we work through these examples, 5 by 5 and 7 by 7 magic squares, think about the answer to the following question. Is it just a random coincidence or a lucky happenstance that we have the number 5 that sits in the middle of our parent square and takes the central square. And what is number 5? Well, number 5, let me write it down carefully over here. Number 5, I'll write it in green. Number 5 is what? In reference to the constant of the magic square of order 3. What is it? Well, it's 15 divided by 3. And what is 3? 3 is the order of the magic square that we're dealing with. So obviously this is not too much material, but as a hint, we can generalize this idea and think what? That the number that sits in the central cell of every magic square potentially has which value? Well, it should be, we think, hypothesize Sn divided by n. True, false, yes, no, maybe. Think about it. Meanwhile, we will move on to a demonstration of the application of the Bachet algorithm to a magic square that is 5 by 5. Because in the previous segment we were very slow and thorough, in this segment, as we apply the Bachet algorithm to a magic square of order 5, we will move in a little bit more expedient fashion. Because the order of our new sample magic square is 5, it can be represented according to the division algorithm theorem. Which way? As 2 times m plus 1, it can be represented as 2 times 2 plus 1. That means that our integer, suitably chosen integer m, is equal to 2. This way we know right away in the second step of the Bachet algorithm how many layers we will have in our pyramids. Exactly 2 layers. And we want also to compute the constant of this magic square of order 5. That is not that difficult to do. That constant will be 5 times what? 5 squared plus 1 over 2. And that computation is not that difficult. 5 squared is 25. 25 plus 1, 26. 26 over 2 is 13. 13 times 5 is exactly 65. This is the constant of a magic square of order 5. And remember our prediction, fearless prediction about the contents of the central cell of a magic square of an odd order, because we know since the numbers here are odd, there's always a central column that has exactly the same number of columns to its right and to its left. There is always a central row in such an odd ordered square, which has the same number of rows on top and below. And the intersection of the central column and the central row produces exactly what? Produces exactly the central cell of our parent magic square. And our fearless prediction that the contents of this central cell will be what? Recall from the previous segment we said that it will be the sum S5 divided by 5, Sn over n. And again, this is not the finite symmetric group S5. Again, this is the constant of the magic square of order 5. So that number comes out to what? 65 over 5. This is 13. This is our fearless prediction that no matter what we do, no matter which choices we make in the upcoming steps of the Bachet algorithm, the number 13 will sit in the central cell of this square. As such, the first step I already carried out. To save us some time, we constructed an empty 5 by 5 square. Step number 1 is done. Step number 2, we already know that since m is equal to 2 in the representation of the order of the given magic square, we'll have 2 layers. So what do? The bottom layer will have, remember from the previous segment, 2 times m minus 1. 2 times 2 is 4. 4 minus 1 is 3. So we'll have 3 squares in the first layer of our pyramid, which are positioned symmetrically with respect to the central column, like so. This will be our layer number 1. And just to give you some visual clues that this is outside of the box, this I'll put some dots over here. And in the second layer of this pyramid, we will have what? 2 times m minus 3. 2 times 2 is 4. 4 minus 3 is 1. one and final square terminates this pyramid. This is our odd diminishing pyramid. And remember, for every side of the parent magic square, we carry out this step. So we construct these pyramids on each side of our square. We do it like so. These are our helper pyramids. They run like so. Game over. This is our helper pyramids. Again, just to show you that visually, this is material that sits outside of the box. This is exactly the manifestation of the expand and conquer problem solving approach, the scope expansion, or expand and conquer. We see that this is the material that sits outside of the box. This completes the step number 2 of the Bachet algorithm. What is the step number 3? The step number 3 says that out of 4 constructed odd diminishing pyramids, we pick one. Which one does not matter. Let's pick, for demonstration purposes, an awkward one. We'll definitely not do the top. We'll definitely then not do the bottom. Let's pick the right one over here. This one. Here in this pyramid, we begin with the sole square in this pyramid, and now we have another freedom of choice. We can go in the direction southeast to northwest, or we can go in the direction northeast to southwest. Let us pick something that some people will say uncomfortable or awkward. Let us go this way, from southeast to northwest. So we mechanically, again, in this step, we mechanically fill out the consecutive numbers diagonally, skipping every other diagonal. As such, all the numbers that are positioned outside of the parent magic square are shown in red, and all the numbers that are positioned inside the magic square are shown in yellow, and all the numbers that will be positioned inside the magic square as we fill out the numbers diagonally, they're static, they're immovable, they are in the right place already. The only numbers that will be moved are the numbers that are outside of the magic square and the ones that are portrayed in red. As such, 1 outside red, 2 outside red, 3 inside yellow, 4 outside red, 5 outside red. No more squares. Reset. Skip this diagonal. Start with the next one. What's the next number? 6. So 6 outside red. What's the next number? 7 inside yellow, 8 inside yellow, 9 inside yellow, 10 outside red. What's the next step? Skip this diagonal. Start with this one, the lower right diagonal. These numbers will be inside. 11, 12, and looky look, 13, exactly as we predicted. The mean arithmetic seems to be 13 in this case, and boom, it sits exactly in the central cell of our magic square. Keep rolling. 14 inside yellow, 15 inside yellow. No more material. Skip this diagonal. Start with this one. What's the next number? 16. Outside red. 17 inside yellow. 18 inside yellow. 19 inside yellow. 20 outside red. What do we do next? We skip the next diagonal. We start with the one that's available, the next one. What's the next number? 21. Where is it located? Outside of the parent magic square. Which color we use? Red color. 21. The next number, 22. Outside red. Next number, 23. Inside yellow. Next number, 24. Outside red. And the last number, 25. Outside red. Again, this completes our step number 3, and we move on to the step number 4. What does the step number 4 of the Bachet algorithm for generating arbitrary magic squares of odd orders prescribe us to do? That step prescribes us to roll through all the numbers that are located outside of the box or outside of the parent square and move these numbers, and only these numbers, inside the magic square. According to which rule? All the numbers that are positioned above the top and below the bottom border of our magic square are translated which way? Are translated horizontally along the proverbial y-axis by how many squares? By 5 squares exactly. And all the numbers that are located to the left of the left and to the right of the right borders of the square are translated which way? Horizontally along the proverbial x-axis by the same 5 squares. Let us translate, let's say, start with the number 5. We translate it by 5 squares vertically like so. 1, 2, 3, 4, 5. Boom. Number 5, actually let's write it in yellow. Number 5 in yellow takes its final resting place, so to speak. So 5 is done. What about number 10? Same thing. Translate it vertically along the proverbial y-axis by how many squares? By 5 squares. So we take number 10 and count. 1, 2, 3, 4, 5. Bam. Number 10 takes its spot. 10. Done. Let's do number 4. What do we do with the number 4? Translated by 5 squares, which is numerically equal to the order of the parent square, vertically, like so. 1, 2, 3, 4, 5. Bam. Number 4 takes its position. So we're done with the numbers 4, 5, and 10. Let's do the bottom numbers over here. 16 translated 5 times also vertically, but this time inside the square upward. 1, 2, 3, 4, 5. 16 goes over here. 21 translated 5 squares. 1, 2, 3, 4, 5. Bam. 21 goes inside. 22. 1, 2, 3, 4, 5. 22. So we're done with the top and the bottom numbers. Let's fold the numbers to the left and to the right. Same way. 2 translated horizontally along the proverbial x-axis 5 squares. 1, 2, 3, 4, 5. 2. 1. 1, 2, 3, 4, 5. 1 goes here. What about 6? 5 squares to the left. 1, 2, 3, 4, 5. Goes over here. Done. And with the numbers 20, 25, and 24, it's easy. We can basically pick up them as a triplet, move them in, and we know the answer. 20 goes here, whereas 25 goes here, and 24 goes here. Voila, problem solved. A magic square is generated. A magic square of order 5 is generated. We made a series of seemingly random choices, 1 out of 4 pyramids times 1 out of 2 possible directions. Still, 13 is the central cell of our square, carries the number that seems to be the mean arithmetic of 65. 65 over 5 is 13. And that is the value of the central cell of our square. Before we move on to the process of constructing a 7 by 7 magic square, I would like to make one suggestion for you guys. You can apply it to the previous case too, 3 by 3 square. And again, the reason I keep these numbers here in these colors that are located outside, and this is the good exercise, reverse engineer this process. In other words, write these numbers first, take this magic square as if a mathematical oracle handed it to you, and then unfold these numbers as shown over here. For example, the number, which one? Number 5 goes over here, number 10 goes over here, number 4 goes over here, and construct this basically an image of the step number 3, what we do in step number 3 when we fill out these numbers diagonally this way, and see how that process works. Now that we understand how the Bachet algorithm works when it's applied to a 5 by 5 square, let us apply that algorithm to a 7 by 7 square. In this segment, we will apply the Bachet algorithm to a magic square that is 7 by 7 in size, and we will do it in even more expedient fashion as follows. 7 as an odd number according to the division algorithm theorem can be represented which way? 2 times m plus 1 or 2 times 3 plus 1 as an odd number. M in this case is 3. We know that in the second step of the Bachet algorithm, we will have how many layers in our pyramids? We'll have 3 layers, m is equal to 3. The constant of this magic square 7 by 7 is what? 7 times 7 squared plus 1 over 2, 7 squared 49, 49 plus 1 50, 50 over 2, 25, 25 times 7, 140 plus 35, 175. And our fearless prediction that the central cell of our magic 7 by 7 square, no matter what choices we make in the upcoming Bachet algorithm, will contain the number what? They contain the number of mean arithmetic, or 25, 175 over 7, 125. And now we roll through the Bachet algorithm. Step number 1, construct an empty 7 by 7 square as we explained, with an equally sized n square cells in it. Step number 2, construct the odd diminishing pyramids on each side of the 7 by 7 square according to which algorithm? Remember, we start with the base that sits on top of the corresponding square, skip one square from each side, roll through the remaining squares, construct them, step up, skip each square from one side, roll through the remaining squares, construct the square, and so on until one square remains. All the material that sits outside of the square is shown in red, and that is what we do in step number 3. Out of 4 pyramids that we constructed in step number 2, we pick one. In such a pyramid, we pick one square as our starting point. I decided to go with this one, and again, for demonstration purposes, I decided to go in this direction from southwest to northeast, and we fill out the numbers mechanically, consecutively, in the fashion: fill out the diagonal, skip a diagonal, fill out a diagonal, skip a diagonal. So here we go: 1, 2, 3, 4, 5, 6, 7, skip a diagonal, 8, 9, 10, 11, 12, and so on. Fill it out that way. That's the step number 3. In the step number 4, all the numbers that sit outside of the magic 7 by 7 square, we do what? We translate vertically along the proverbial y-axis if these numbers are above the top and below the bottom borders of our square, and all the numbers that sit outside of the parent magic square, that is 7 by 7, to the left of the left and to the right of the right borders, we translate horizontally along the proverbial x-axis, and voila, the square is complete. For example, let us say we work for demonstration purposes with the number 1. By how many squares do we translate that number and all the other numbers? By the number of squares that is equal precisely to the order of the square, or 7. Thus, we grab this one number and we carefully count: 1, 2, 3, 4, 5, 6, 7. Bam! Number 1 translated horizontally. Let's pick any other number. Which one do you want? Some awkward number. 43. 43 sits over here. We grab that number and we translate it vertically along with the direction of the proverbial y-axis inward into the square. By how many squares? By 7 squares. Grab it. 1, 2, 3, 4, 5, 6, 7. Bam! Number 43 is in its final resting place. And voila, we repeat this process for all the numbers that sit outside of the parent magic square. And by the time we're done with all these numbers, we have a magic square of order 7. All the numbers in each row, all the numbers in each column and along both diagonals sum to one and the same number, known as the constant of the magic 7 by 7 square. And the contents of the central, let me highlight it in green, the contents of the central cell of that square is, as we predicted, the mean arithmetic of the constant 175 over 7 is 25. And before we call it a day with the Bachet algorithm, I want to say 2 things: that there is a way to obviously prove with all the mathematical might and rigor that the Bachet algorithm is correct, but I would urge the members of our community to be careful what they wish for, because it is possible to show this in public setting that the Bachet algorithm is correct, that demonstration will be nothing but non-stop modular arithmetic, and in my rough guesstimate, it would require from a cold start about 5 one-hour lectures, 5 one-hour episodes, because we will need to cover the greatest common divisor, the division algorithm, the basics of the modular arithmetic, the linear congruences, and then the proof that once we construct two such congruences, the determinant that pops out from these congruences satisfies this or that condition. We troll the Bachet algorithm through these 4 conditions that pop out of this proof and show that this proof is valid and correct, that this algorithm is valid and correct. What we can do in the public setting is using the sample 3 by 3. I will not be doing it with 7 by 7 and 5 by 5, but with the 3 by 3 magic square, we will demonstrate precisely this observation that we made earlier. We will show in the next segment that given an arbitrary 3 by 3 magic square, the contents of the central cell of that square will be precisely the ratio of the constant Sn of that square divided by the order of that square. In this segment, using a 3 by 3 magic square as a sample, we will show that if S is the constant of such a 3 by 3 magic square, then the contents of the central cell of that square must be S3 divided by 3. Precisely, whatever the constant of the magic square that is 3 by 3 in size is chosen to be. To that end, we number the elements of our, or the entries in our 3 by 3 magic square as shown to the left on your screen: A1, A2, A3, A4, A5, and 6, and so on. This is number 7, just to be sure that this is number 7. And here is one way to do it. First, for a first take, we will work our way, for example, vertically like so, and through a diagonal like so. In other words, we write down the one of the conditions for the numeric square to be the magic square. So we write down A1 plus, I'll use the green chalk for now, A4 plus A7 is S, the constant of the square, A1, A4, A7. If we sum this column, we get the number S. Here we'll use S. And if we sum all the numbers along the main diagonal, we also get S. In other words, if we write down A1 plus what? A5 plus A9, we also get S. What do we do next? Well, we exercise the symmetry. We work this way. This will be S, and we work along the secondary diagonal S over here. For the first one, what do we have? We have A3 plus A6 plus A9 plus A9 will be S. So far, so good. And then for the secondary diagonal, what do we have? We have A3 plus A5 plus A7 plus A7 is also S. There's nothing outlandish or controversial over here. We simply spelled out several of the conditions that make a numeric square a magic square. Now we exercise the fact that A1 on both sides is one and the same, and here is A3. The element A3 is one and the same. What does it mean? From this equation, it follows that A4 plus A7 will be S minus A1. And from this equation, it follows that A5 plus A9 will be S minus A1. That means that this sum is the same as this sum. So what do we write? A4 plus A7 is equal to A5 plus A9. Would you agree? We pull the same maneuver with this system of equations. A3 is one and the same element. Subtract from both sides, have S minus A3, S minus A3. Same thing. So that means that here it's this sum and this sum must be the same. So what do we write? we write a6 plus a9 is the same as a5 plus a7. Would you agree? Yes, it looks like I didn't make any silly typos. So now what do? Well, we sum these two guys side by side, left hand side and the right hand side. What do we get on the left hand side of our result? Let us see. So we get a4 plus a7 plus a6 plus a9, which is what? 2 copies of a5, 2 times a5 plus a7 plus a9. Would you agree? So far so good. Now we witness what? Favorable cancellations. a7, a7, goodbye. a9, a9, goodbye. What do we have left? a4, let's write it down over here. a4 plus a6 is equal to 2 times a5. You see this? a4 plus a6 is twice the value of a5. What is missing in this conclusion, in this string of symbols? Let's look at a4 and a6. Where is a4? Here is a4. Here is a6. They sit in the same row of our 3 by 3 magic square. What does it mean? It means that the monkey in the middle, a5, is missing from here. So we add a5 over here, plus we add a5 over here, plus, and what do we have? Let's jump over here. What do we have? Well, we have the sum. This is our sum, right? Remember, one of the conditions for a numeric square to be a magic square, the sum of all the numbers in any given row of that square must be what? Must be the square's constant. So we write down S is equal to thrice the value that sits at the value at the central cell of our magic square, a5. And from here it follows what? Well, it follows that a5 is S of 3 divided by 3. Statement proved. And again, remember that in every square that has an odd order, the central cell always exists, because we already explained why. All the columns in such a square can be partitioned into what? Central and the same number of columns to its right and to its left. And all the rows in such a square can be partitioned into what? A central row with the same number of rows below and above. And the intersection of the central row and the central column leads exactly when two straight lines intersect at a point. They produce the central cell of such a square. This is just one proof, and I'll take a short break right now and erase this material. I'll use a chalk of different color, and here, instead of going vertically and diagonally, we will go which way? Precisely, we'll go horizontally, but still diagonally. This segment is optional. It's for curious travelers only, because this segment we will show that if we work with our 3 by 3 magic square horizontally, so to speak, we still will prove that the contents of the central cell of such a square must be the mean arithmetic of the constant of that square, or S over 3. As such, I will use a different color this time to make it easier for you guys to see, but with this computation shown in yellow, we will work horizontally like that. Sorry, this job doesn't seem to work anymore. This way, with the top row, and the bottom row, like so, will work this way. So from this sum, if we sum all the elements in the top row of our 3 by 3 magic square, what will we have? We will have a1 plus a2 plus a3 must be what? It must be the constant of our magic square. And if we work diagonally, again, still from the same for the main diagonal, we will have a1 plus a5 plus a9 will be the same sum as. Now here we switch gears a little bit and we work with the bottom row of our 3 by 3 magic square. From that bottom row, if we sum all the numbers in the bottom row, we must have, by definition of flipping a numeric square into a magic square, have one and the same number s. So here it will be s and here it's s. So what do we have? a7 plus a8 plus a9 will be the constant of our square. And again, we can sum the numbers along the second diagonal. Numbers commute under addition. It doesn't matter which way we write it. We can write it down actually this way, a7, so it's easier for us to see. a7 plus a5 plus a3 is the sum s. Okay, let us loiter around this pair of equations. Here we have the element a1 and a1 is the same. Subtract a1 from both sides. This sum of elements 2 and 3 will be s minus a1. And this sum of elements 5 and 9 will be also what? S minus a1. That means that a2 plus, let's see, a3 is the same as a5 plus a9. So far so good. Same maneuver applies over here. a7, a7. This sum is the same as this sum because they both of these sums equal to what? S minus s, a7. So here we write a8 plus a9 is the same as a5 plus a3. Would you agree? This is dead. So what do we do now? Well, we do the same thing. We add the left-hand side of this equation to the left-hand side of this equation and the right-hand side of this equation to the right-hand side. What do we have? Let's spell it out carefully. a2 plus a3 plus a8 plus a9 is the same as what? a5 and then 5 twice the element a5 plus 7, 5 and 3 plus, what is this? Plus a3 plus a9. Would you agree? Yes, this is a string of symbols that we obtain if we add this equation to this equation side by side, left-hand side to left-hand side, right-hand side to right-hand side. And what do we see again? A wave of favorable cancellations, which are a3 on the left-hand side and a3 on the right-hand side are no longer needed. And then the 9s, the a9 on one side and a9 on the other. What do we have as the sole survivors on the left-hand side of the equal sign? a2 plus a8 is equal to twice a5. And let's again analyze the numbers a2 and a8. Where are they in our magic square that is 3 by 3? a2, a8, this way. So what's missing? The monkey in the middle, a5. So we add a5 to the left-hand side. We add a5 to the right-hand side. What do we have over here? Well, here we have our favorite number s, which is the constant of this 3 by 3 magic square. So this is s. And what do we have on the right-hand side? Again, 3 times a5. From here, it follows what? That the value that sits in a5 is our sum associated with the magic square, 3 by 3, the constant of that square divided by 3 or by the order of that square. And in like fashion, you can try your hand at showing that this idea holds true, for example, for a 5 by 5 magic square. And if you will number these numbers, if you will number the entries in the 5 by 5 magic square evidently the same way, let's say what you will have the number called a13, in the middle, and if you exercise, if you go through similar manipulations, then you will have what? You will have 4 copies eventually of A13 on one side, and almost all the numbers that sit along the central column or the central row. And if you add the missing number, you will have precisely 5 copies of the constant of the 5 by 5 square, and so on. Again, this is always possible. Why? Precisely because the order of all the squares is odd, and the central column and the central row always exist. Their intersection produces the central cell, and the contents of the central cell obey this little theorem. This is it for the Bachet algorithm, and we will look at a new challenge next. Our next challenge, the mathematical problem S2M32, will be the final challenge which we use in order to conduct a dedicated study of the scope expansion or expand and conquer problem solving approach. And in that challenge, we are asked to evaluate the following indefinite integral. E, the base of the natural logarithm raised to the power a times x times the trigonometric function of sine evaluated at the argument b times x times the trigonometric function of cosine whose argument is c times x, and the entire integration is carried out with respect to the dummy integration variable x. And a, b, and c, a, b, and c are constant real numbers. And again, because precisely we're studying the mechanics of the scope expansion or expand and conquer problem solving approach, it is suggested that you, of course, do not use, for example, integration by parts to evaluate this integral, but find a way to perhaps counterintuitively add more material to the problem at hand, but derive a tactical advantage and evaluate this integral in a straightforward manner. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2M32.